What if I tell you that you could reduce your plant's energy cost just by smartly designing your heat exchanger network? Today, we are diving deep into heat exchanger network or HEN design using Aspen Energy Analyzer, but we are not stopping here. I am going to show you exactly how varying your hot and cold utilities impact your overall process performance, and we are going to use MS Excel to crunch the custom financial data to prove it. Hello everyone, welcome back to Chemical Engineering and Aspen channel. If you are chemical engineering student, researcher or process engineer, this video is going to be extremely valuable for you. Today we are diving into heat exchanger network design using Aspen Energy Analyzer, and more importantly, we will analyze how variation in hot and cold utilities impacts overall process performance. Plus, I will show you how to replicate key calculations in MS Excel so you are not just clicking buttons, you actually understand what's happening behind the scenes. Let's start with the problem that we have a process in which there are multiple hot streams and multiple cold streams. There are actually two cold streams, number 1 and number 3, and two hot streams, number 2 and number 4. We are given their supply temperatures, their target temperatures, the heat capacity, flow rates. And obviously we know we can calculate the value of Q from them. Our goal is simple but powerful. Minimize external utility consumption, maximize heat recovery within the process. This is where pinch analysis and Aspen Energy Analyzer come into play. So we have been given the data of 4 sets of utility which we will be varying today, that we will be using cooling water and air in the system, and accordingly HP steam and hot oil in the system. So the first combination include cooling water and HP steam as cold and hot utility respectively, then cooling water and hot oil, then air and HP steam, and then air and hot oil. So we will now move to Aspen Energy Analyzer and we will perform our calculations, and then we will vary the utilities to see the impact on the overall process performance. This is the same example which we have performed today earlier. So I have put the data over here that H1 is from 170 to 60 degrees centigrade. The total heat load is 330 kilowatt. H2 150 to 30 degrees centigrade. Total heat load is 180 kilowatt. C120 to 135 degrees centigrade. Total heat load is 230 kilowatt. And C2 is 80 to 140 degrees centigrade. Total heat load is 240 kilowatt. And if we look at the targets, the heating load requirement is 20 kilowatt. The cooling load requirement is 60 kilowatt for the value of delta T minimum as 10 degrees centigrade. The hot pinch temperature is 90 degrees centigrade, while the cold pinch temperature is 80 degrees centigrade. Even we have this data in Excel as well. And if you remember previously that we have calculated these values both manually and using Aspen Energy Analyzer. But our objective today is to vary the utilities to see its effect on the performance of the system. So for the first case, we have taken HP steam and cooling water in the system. So this is our first case. Then we will vary the cold utility from cooling water to air. Then we will vary the HP steam to hot oil. And if I take you to the heat exchange network diagram, actually I have built it beforehand for you to understand that the H1 and C2 both are exchanging heat with each other and consuming the process. Like it has to go from 170 to 90 degrees centigrade, and it has to go from 80 to 140 degrees centigrade. Its heat requirement was 240 kilowatt, while its heat supply was 240 kilowatts, so that both matched. The delta T on both sides is also visible. Then we connected H2 with C1, and you can see it has moved from 80 to 125 degrees centigrade, while the ending temperature of this stream is 135 degrees centigrade. So to move it or to increase its temperature from 125 to 135 degrees centigrade, we needed a utility. Obviously, we have used HP steam, and 20 kilowatt duty exchanger is applied. This is the utility exchanger, and these two of gray color are the process to process exchangers. As I have told you, we want to minimize the external utility. How we have minimized? By ensuring process to process heat recovery. So this was the above pinch region. If we go to the below pinch region, we have first connected the stream H2 with C1. That C1 goes from 20 to 65 degrees centigrade, and in that case the H2 is completely consumed as it has gone from 90 to 30 degrees centigrade. The delta T at this side is 10, at this side is 25. Then we connected the second exchanger. It goes from 65 to 80 and its requirement is fulfilled, while it has gone from H1 has gone from 90 to 80 degrees centigrade, 15 degree centigrade delta T this side, and at this side it is 10. The minimum delta T is 10, so it is applied or it is followed at each point in the exchanger. And to take it from 80 to 60 degrees centigrade, obviously we now require the utility, so that is the cooling water, and 60 kilowatt duty exchanger is applied. So you can see that 20 kilowatt heating and 60 kilowatt cooling load is required for the delta T minimum of 10 degrees centigrade, and we have minimized the utility consumption, we have maximized the process to process recovery. One of the simplest way or the conventional way was to apply cooling utility to H1 and H2 and to heating utility to C2 and C1. But that was a costly method, that was the infeasible method, and that was a traditional approach. But in the professional approach, in the sustainable approach, we have to maximize process to process recovery, and then you can see we are left with very few amounts of external utility requirements. Now this is the overview of overall process, and if you see, if I take you to the network cost, that the heating cost is 100% of the target, cooling is also 100% of the target, operating is also 100% of the target, capital is less than the target. So the percentage of target, it is 97.3%, and the total cost is 97.4%. So this is the first case which we have studied. Now I will vary cooling water with air, and we can see, we will go back again and we will click on this, and now you can see these first 3 points are 100 as of the first case, but now the capital cost and total cost have been increased, that you have crossed the limit or you have crossed the barrier or the benchmark, because 100% means that if there's a benchmark of 1, you are at 1, but if it is above 100%, it means you are above one value. So you can see that the capital and total cost has exceeded, and this is obviously not the reliable or not the suitable case. Going to case number 3, changing it with hot oil. Again, going back to the network design, again clicking the view, and now you can see that the capital cost and total cost are significantly reduced, even if we compare with the case number 1, where cooling water and HP steam was used, that 96.17%, and this is 96.31%. So this is our case 3, which at far moment looking like the best case. And going to the last case of hot oil and cooling, and coming back here and clicking on this network cost view, you can see it is also not the best case, because capital cost is 107% and total cost is 106.6%. So anything above 100%, obviously we do not want it. Obviously we want to maximize our savings, maximize our energy potential, but obviously at the expense of minimum cost. So these are the 4 cases which we have discussed, and if I take you to the Excel sheet, and if I look at the comparison, that HP steam cooling water, you can see this one, because these points are also all 100%. So these are not involved in the comparison. The main thing is the capital cost and the total cost. So for HP steam cooling water, it is 99.69 and it is 99.7. It is 106.65 and it is 106.45. So these are not obviously understandable or efficient. Similarly, hot and cooling water, not okay. But you can look at this case of hot oil and air, you can see it is 96.17 and it is 96.31. So that shows that designing the same network for different set of utilities we can obviously optimize based on our utility selection. And you can see that the utility selection is critical once we are talking about the economics. So designing a heat exchanger is not just about matching lines on a screen, it's about understanding how your utilities dictate the entire financial reality of your plant. By combining the thermodynamic power of Aspen Energy Analyzer with the financial flexibility of Excel, you are basically unstoppable. So in this video, you have learned how to design a heat exchanger network using Aspen Energy Analyzer, how utility variation affects process performance, and how to validate everything using Excel. If you are serious about process optimization, this is a must-have skill. If you found this helpful, like the video, comment HEN and I will share the Excel template. Subscribe for more advanced chemical engineering tutorials. And if you want, I can also make a follow-up video on economic optimization of delta T minimum. See you in the next one. Goodbye.